Hello, here's another Newton's second law question. We got a ship of mass 5,000 tons, so a ton is 1,000 kilograms, is a metric ton. Two tugs used to pull the ship using cables that are horizontal. Right, I'm imagining this description is going to look like this. It's going to describe the diagram, so let's just see. We've got a tug exerting a force of 100,000 newtons at an angle of 25 degrees, yeah, and another at T newtons at angle 20. So yes, so they've just described the picture, which they normally do on these. The ship accelerates in a straight line along its center line, right? So our acceleration is going that way. Find T. Okay, right. So we got a two-dimensional space going on here. I know it's only moving in one direction in a straight line, but the forces are operating off of that straight line. So we've got a two-dimensional setup. We can set up something like this. We could say that's an I direction and that's a J direction. And then we can resolve in those directions and apply Newton's second law. So we're going to have Newton's second law, and then we're going to resolve in each direction. So we'll start off by resolving in the J direction because it's told us that it's moving in the I direction. So in the J direction, there is no acceleration. So using our F equals ma in the J direction, we can say that we've got 100,000 multiplied by sine of 25 degrees. So that's in the positive J direction. That's the component of this bit in the positive J direction. And then for the T newtons, that'd be negative. So we've got minus T times sine 20 is equal to 0. So these things must be equal to each other. And we've got that T is 100,000 sine 25 degrees divided by the sine of 20 degrees. And that is, tapping it all in, 100,000 sine 25 divided by sine 20, 123,565 newtons. So they've given us some pretty rounded numbers on here, so we don't want to get too carried away with the accuracy. So I'll stick it down as 124 kilonewtons. So that's sorted out the first bit. And usually we're going to want to resolve in the other direction as well. So let's see what they're asking us in the second part. Got a resistance force of magnitude 20,000 newtons directly opposing the motion of the ship. So find the acceleration. So yeah, pretty much as was expected. We've got 20,000 newtons going in the opposite direction. And we just need to resolve again. So we can resolve in the I direction. And that is going to give us that we've got 100,000, I've got the right number of zeros, yeah, times cos 25 degrees, plus this time T, well, yeah, whatever that was. So yeah, I might, let's use the original number. So 100,000 sine 25 degrees over sine 20 degrees, that's our T, using the accurate one, multiplied by cos 20 degrees. Of course, you can use that T that you've already got sitting in your calculator. I've just written it out again for completeness. I've got to take off the 20,000, so that's going in the other direction. And that is going to be equal to our mass of 500 tons, so 500,000 kilograms multiplied by the acceleration. So we just got to type all of this in, and then and then that's going to give us what A is. We do calculate all the left hand side divided by 500,000 and typing it in while I'm jabbering on, we get the acceleration is 0.373 meters per second squared. Again, it's debatable as to how accurate we want to give these answers. So yeah, whether you want 0.373 or we could have had this at 120 kilonewtons. I mean, these are all very woolly numbers we've got sitting around here. Anyway, that's the general process. You see, as much the same as we had before with the warm-up questions. Exactly the same method we're using. They've just put it into a little bit of context here. I find it useful when they give you a picture. So they've given us this diagram here, and then when you're reading through the question, don't just read through the information in the question separately from the diagram. So and see, well, what have they given us on the diagram? Is this description just a straight description of the diagram, or is there anything that's missing? Like the one thing they hadn't mentioned in the diagram that's in the text is this 500 tons bit. So you might want to write on something in here. You could put in the 500,000 kilograms on the boat and add that in as you're going through, or highlight it as the one thing that's not on the diagram. Because it's just nice to match these things up as you're going through. Otherwise, you read it all and then you look at the diagram and say, oh yeah, is there anything missing? You might as well be doing that while you're going through it. So yeah, a nice opener then for a Newton's second law exam question.